Our next speaker is Nikos Zygouras from University of Warwick. He will talk about SPDEs and criticality.
Okay, thank you. Thanks a lot. Yes, when I received the invitation from Hendrik and AJ about this meeting, I was extremely happy, both because I would see so many people who used to be at Warwick that now they left me alone. They remind me all those nice moments we had there. But also because, yes, I think this is a really exciting direction of, bridging mathematical physics and stochastic analysis. So, I was very excited to be able to come here, and thanks for this. And yeah, I realized also there is no talk that has all three topics, which is also a very good thing, which means that it's an emerging field. So my talk is going to touch two of the three parts of the conference, sort of some SPDEs and stochastic analysis and criticality. And yeah, we'll present some examples where we see the emergence of criticality. And these are the examples are going to be centered around works I have been doing with my good friends for a long time now, Francesco Caravena and Rongfeng Sun, and some new friends here. One of them is embarrassed with a big smile, both of them. I think here we are. Sorry?
I said I'm not that slim.
So yeah, you can see the difference. Big smiles here, less smiles here. I think that was a day after we were very stuck. But these guys are powerful and always big smile. And yes. Okay, so let's go ahead. So the central example I'm going to discuss is stochastic heat equation. So I guess many people, everybody here knows, you have the heat equation perturbed by a multiplication of white noise, space-time white noise. So I'm going to talk about space-time white noise. You can also consider only space white noise, but it's more difficult indeed. And here I'm going to talk about space-time white noise. So all the noise that appears everywhere is space-time, multiplied by the solution of the equation. And criticality emerges when you look at the dimension 2. And the way I see the emergence of criticality is that if you scale parabolically the solution, then you get a new scaled stochastic heat equation where the scaling parameter appears here in front of the noise and the product. And right, so when d equal 2, you see the exponent here vanishes. When d is bigger than 3 and epsilon goes to 0, so yes, the effect here of the noise goes away. And when d is equal to 1, so the effect of the noise becomes strong. In statistical physics, people are interested in large scales. So you see, divide here t by epsilon squared, and you let epsilon goes to infinity, to 0. So you see correlations at very far points. And in stochastic analysis, people would be interested to take epsilon go to infinity, no matter, it's epsilon going to infinity. This is absurd, right? Epsilon should be always small. But this is interesting about the short scale correlations. And yes, so when epsilon goes to infinity and d is 1, then this thing kind of goes away. So the picture of stochastic analysis and statistical mechanics is sort of dual to each other, right? We have an agreement. Okay. So yes, in the SPDEs, so the two things is that in disordered systems, actually what in SPDEs and it's usually called criticality is called marginality. So it has to do with the disorder and whether disorder becomes relevant or disorder becomes irrelevant. And when you are at a critical, so disorder becomes marginal, so it can be marginally relevant or marginally irrelevant, and one has to look at things much, much more carefully. Okay, so let's move, now starting treating away from the heuristics and starting treating things more rigorously. So you see the U epsilon here, the epsilon here appears in the subscript, compared here that it was superscript, because the two U epsilons are different. And here what I mean is that I mean by U sub epsilon to be the solution of the stochastic heat equation, where I have mollified the space-time noise so that I have a well-meaningful solution to this equation. I space-time mollify in this fashion. And here I also enter the noise parameter, which also has an indicator epsilon. So in dimension one, okay, so the goal here is you mollify the equation, and then you remove the mollification, and then you want to ask, okay, can you establish a meaningful limit for U epsilon? And can you describe this? In dimension one, it turns out that you just need to have this beta as a constant, and you can obtain a meaningful limit. At a critical dimension, correlations become stronger, and you can only make sense if you also need to start dampening the beta epsilon going to zero, and you have to do this in a very particular way. You have to dampen it in this logarithmic fashion, and the emergence of logarithm is going to come maybe later. And right, so here you have something that goes to zero, and then you would naively say, okay, the whole thing just goes away, but that's not what happens. So you have something that goes to zero. When you remove the mollification, the noise starts becoming infinity. So you have the problem 0 times infinity. What is 0 times infinity? Okay. So we will see that in the critical dimension, 0 times infinity gives something that is non-trivial. It's not zero, it's not infinity. It's something that is a new object. Okay, so that will be the setting I'm going to work with. But yeah, so a first result in this direction was obtained a few years ago with Francesco and Ronfeng. And then we looked at both 1-point fluctuations of the limit of U epsilon, and also the correlations, the field. So the first result is that if you fix any space-time point, and you look what is the limit of the solution of the mollified stochastic heat equation, you observe a phase transition. And this phase transition was something that was not anticipated. So if you are below this, okay, so let's go back to recall what is beta hat here. So beta hat is what appears in the strength of the dampening of the noise. So you dampen the noise like 1 over square root log epsilon, but you also have this extra parameter beta hat. When beta hat is strictly less than 1, then the solution converges to an exponential of a normal variable. So it has a log normal distribution at the end. And the strength of this, the fluctuations of this in front of the normal are given by this logarithm. So you already see here that when you hit beta hat equal 1, the fluctuations become very strong. And actually this has the effect that the solution will converge at any point to 0. So if you pick any point of your space and time, and you ask what is the limit of the stochastic heat equation, you will just see 0. Okay. But there are more interesting things happening when you look at it as a field. So you may be 0, but maybe at some point you have some peaks. Okay, and you would like to understand this structure of the measure. When beta hat is strictly less than 1, we have this theorem that, okay, asymptotically, the solution will kind of, in terms of correlation, will become flat. It will not be 0. It will be sort of when you start averaging, the law of large numbers kicks in because the solution decorrelates. So when you average some field which decorrelates, then you see the law of large numbers. Okay. So this one corresponds to the law of large numbers, and it's also the solution of the heat equation, right? With the solution of the heat equation. But if you magnify the fluctuations around the law of large numbers by square root of log 1 over epsilon, then the solution converges as a field to the solution of the additive stochastic heat equation. And what's interesting here is the prefactor of the noise. So here is a new noise. It's not the original noise that I had. Actually has a component which is independent of the original white noise component. And there is a non-trivial strength here. And actually I highlight this because I think this is something, yes, I would like to understand a bit better in general. So we will see this occurrence of different noise emerging with different variance strength in a number of examples. So actually, so if we go back, I mentioned here that you have something going to 0, something going to infinity, and the question is what is 0 times infinity? And here we see that 0 times infinity actually gives an independent, a noise which has an independent component from the original driving noise, and this non-trivial variance strength. Okay. Now, I would like to briefly go to some other examples where, I mean, the stochastic heat equation is a foundation, and then this kind of propagates in some other examples. So, two-dimensional KPZ equation, okay, so two-dimensional is always a critical dimension in these models. So, this is a KPZ equation. You can, again, dump the noise by this logarithmic factor. You have the beta hat here. This 2 pi actually is specific to the model. So this picture I showed in the previous slide is a kind of universal among different models. And the thing that changes is really this kind of particular constant. And then you will be having the phase transition of this beta hat equal to 1, less than 1, or greater than 1. So this is the two-dimensional KPZ equation. You subtract this infinity. You subtract specific constant that goes to infinity. And then a theorem that we proved with Francesco and Feng about 1 or a bit more later is that when beta hat is less than 1, you have again the same Edwards-Wilkinson limit. Edwards-Wilkinson limit is that the solution converges to the solution of the additive heat equation. Another name for this is a Gaussian free field. Okay. And what's interesting is that, so it will converge to exactly the same thing here when viewed as a field with the same prefactor here in the noise, in the limiting noise. Okay, so around the same time we did this, so a few weeks later, Gu also proved the same result, but not in the whole subcritical temperature regime, in part of, for beta hat very small. And a precursor to our result was a result by Charles and Dunlap, where they looked at this solution and they proved tightness, also in the part of the subcritical temperature regime. Okay. Another example has to do with anisotropic KPZ. So here you change the plus, which was in the isotropic KPZ, to a minus. And an equivalent thing, so what I was doing before was to dump down the noise, but an equivalent thing, because of the scaling properties of the KPZ and the noise, is actually to dampen the nonlinearity. So if you dampen the nonlinearity in this particular ways, you start seeing something non-trivial in the limit. And that is described by works of Erhard, Cannizzaro, Toninelli, and also, yes, some previous works also with Schembauer. That the solution of the anisotropic KPZ equation converges again to an Edwards-Wilkinson limit, where again you have a different diffusivity on the noise, strength of the noise, but also in this case you also have a different diffusivity. One thing that is different than isotropic KPZ with regards to the isotropic KPZ is that here you don't observe any phase transition in this parameter lambda, the strength of the logarithmic dampening of the nonlinearity of the noise. Okay. Another example is a semi-linear stochastic equation. This is works of Dunlap and Gu. So before I was working in a linear setting, and Dunlap and Gu worked where the noise is multiplied by a function Lipschitz function of the solution. And what they proved is that if the Lipschitz constant is less than this critical value, square root 2 pi, so square root 2 pi is the analog of my beta hat less than 1, equal 1. Then they showed that if you look at the solution at this kind of exponential time scales, then you converge to a non-trivial distribution. And in this case, a non-trivial distribution is given by the solution of this forward-backward SD. So that was a very interesting result. In the case where sigma u equals u, you can solve explicitly this forward-backward stochastic differential equation, and then you recover the result we had with Caravena and Sun, that the solution converges to a log normal distribution. So the solution of this equation when sigma is the identity is a log normal distribution. Okay. So this actual exponential time scales is something very important. It was also coming from, I'll come back to this. It's also was first observed in the work with Caravena and Sun in the stochastic heat equation. I'll come back to this later. So it's interesting. So they have this condition about the Lipschitz, the Lipschitz constant should not be too big to have this non-trivial result. But I think there is more to be explored here, because they can also do the case where sigma u is square root u, which is definitely not Lipschitz. So it's an interesting, so the square root u has not been published yet, but they can do it. And this is, of course, relevant because of population models coming from population genetics. So it's interesting to see what is the truth characterization of the subcritical regime in these nonlinear stochastic heat equations. Also, in terms of looking at the solution of this as a field, so this is a one-point fluctuation, but you can look at the solution of this as a field. And Ran Tao, who was a student of Dunlap of Gu, was able to prove again Edwards-Wilkinson fluctuations. And again, you see the strength of this new noise that you get is something non-trivial. Okay. A bit on the Allen-Cahn. So yes, that will be the last part of my talk. So with Simon and Tommaso, we have been also starting looking at the nonlinear models, where we wanted to start, getting into our hands into all these trees, structures, and regularity structures, and so on. And so we looked at this Allen-Cahn equation is not driven by a noise now, but the noise appears as the initial condition, which is also scaled. So again, it's dimension 2. And the noise again scaled in this familiar to the audience, I hope now, logarithmic strength. The motivation to look at this was, we wanted to do something that we start playing with trees, and the motivation was this paper of Martin with Hoale and Tommaso Rosati, where they had you see a subcritical, if you could say, scaling of the noise at the initial condition. So the result that I'm going to allude to later on is that, yes, if you have a lambda less than some particular constant lambda 0, and you multiply by square root of log 1 over epsilon, this solution as a field, so here you should think of it as being averaged somehow, will converge to, yes, the convolution of the heat kernel with the white noise. And again, you get here a non-trivial strength of the limiting variance. And what's interesting is that this strength comes as a solution of an ODE, which you can solve explicitly. So again, understanding the emergence of the strength of the strength of the emerging noise, I think is something interesting to put our hands and understand a bit deeper. Yes.
Here, Your T is kind of fixed.
Fixed, yes.
Log epsilon burden.
Yes, so this is,
It's still very hard.
yeah, so we don't look at large time asymptotics. That would be, yeah, a later goal, because, yeah, I think also the interest in Allen-Cahn is more to look at the long time asymptotics and see these metastabilities. But here was to understand a bit more of the structures of how trees come and kind of, yeah, finite time correlations. Yes, to play a bit, put our hands into the structures. Yes, but definitely, yes, your result goes much further than this thing. Yes. Yeah. We can do so. Simon has informed that you know, we don't need to have a fixed time horizon, but we can have a flexibility on the horizon being like what, 1 over epsilon, is it? 1 over epsilon. Yes, but we haven't looked much into, you know, long time asymptotics. Yes, still there are baby steps. Yes, I hear. Okay, so all these examples that I was talking about was critical dimension, but below a critical temperature. And then the patterns that you always see at the limit as a field, some Edwards-Wilkinson universality, some Gaussian field at the limit. At a critical temperature, the example that we have with Francesco and Dongfeng is the following. So I will be talking about, so here, Z, this is the partition function of a direct polymer model. I'm going to define it in 1 or 2 slides. This is a discretization of the solution of the stochastic heat equation. And then we prompted what happens at, let's say, beta hat equal 1. Okay, so we had seen that at beta hat equal 1, if you look at 1 point, the solution goes to 0. If you start looking at the correlations, the field becomes asymptotically independent at large scales. So then when you average, you get 1 plus 1 over square root log epsilon Gaussian fluctuations. But when you start prompting at beta hat equal 1, correlations become strong. So the field will pointwise go to 0, but then we'll have some peaks, and the peaks will be correlated. So if you now subtract again 1 from the solution, and then you average the starting and the end point, you don't need anymore to multiply by anything growing to infinity in order to see something non-trivial. And what we proved that the field converges to an object which we named stochastic heat flow, the critical 2-dimensional stochastic heat flow. So critical corresponds to the fact really that you are also at the critical dimension, but also at the critical temperature. So here you will converge to a non-trivial field, which is low correlated, but is not Gaussian. So this is one of the few examples of non-Gaussian low correlated fields. But also we proved in a more recent work that is not the exponential of a Gaussian. So what is known as Gaussian multiplicative chaos. So it's not also a Gaussian multiplicative chaos of any sort. This actually is a kind of a useful result in the sense that if you take the logarithm of the stochastic solution, or the logarithm of the partition function in this case, this would correspond to the solution of the KPZ equation. This is an indication, it's not a proof, but it's an indication that the critical 2D KPZ equation is not Gaussian. So some other things that we have proved more recently, but is not published yet, is that so this will have the limit will be a measure. So it's not a function like in the subcritical case. It will be a measure, and it's actually singular with respect to the Lebesgue measure. So it's really this pixel that is kind of 0 and has some peaks. But understanding the structure of the peaks is actually quite interesting, and we would like also others to join forces to understand the structure of this measure in the peaks. Okay. Another thing that we have, yes, we see hints of that come out from the proof that this object has some notions of self-similarity. And maybe I will give a glimpse of this notion of self-similarity here. One other interesting question is that we were asked is that, okay, we proved that there is not the exponential of Gaussian, is not a Gaussian multiplicative chaos, but there is a question whether this can be, whether this is actually absolutely continuous with respect to Gaussian multiplicative chaos. This should not be the case, but you know, we have to understand a bit more the structure. Again, it has to do with the structure of the field, the maxima, and so on, and how they compare with structures and maxima of Gaussian multiplicative chaos. Okay, if there are not any questions about the results, yes.
Is any of this then except for numerical simulation?
Well, actually, that's something I was wondering, you know, how we could simulate, maybe get a picture of the measure. You know, there are some very nice pictures floating around. Unfortunately, I cannot do. You know, there's a recent work by Balint Virag and about parabolic Anderson model. It has this beautiful Mount Fuji picture of, you know, I'm jealous. Yes. So if somebody can do some numerics of this, that would be very nice and very interesting. Maybe Martin, the magician of simulations and yes, software. Yeah. Okay, very good. Okay, some structure, give some glimpse of the structures and the method. So I would like to give you, you know, a glimpse of the structures in the critical dimension, but subcritical temperature, a glimpse of the structure in the critical dimension and critical temperature, and a bit of the structures in the nonlinear models and the, you know, this based on the Allen-Cahn. Okay, so as I said, we would like to go to discrete. We can do, you know, usually we work everything on the discrete, and then we can transfer almost verbatim everything to the continuum. And our you know, test you know, tool is the directed polymer model, which comes basically as a discretization of the Feynman-Katz representation for the stochastic heat equation. So the Feynman-Katz representation is that, well, if you have initial data psi, then you average a Brownian motion B of t starting at x, and times the exponential of the integral of the white noise along the trajectory of this Brownian motion. And then you subtract the quadratic variation of the stochastic integral. The discrete version of this, we replace Brownian motion by random walk. You replace integral by sums. You replace white noise by a collection of IID random variables on each space-time lattice point. And then you have the expectation of, with respect to the random walk of this Feynman-Katz time object. Here, lambda beta is a log moment generating function of the IID random variables, which is basically plays the role of this quadratic variation. Okay, so having this expression, what we do is we do a chaos expansion of this. So this is also can be called as a high temperature expansion. Essentially, you expand the exponential. And in pixels, so if you expand the exponential, the chaos expansion can be visualized in this way. So I'm going to try to decipher this picture. So this is a lattice here, and you pick k space-time lattice points. So one is here, one is here, one is here, and so on. And then the random walk will jump from one place to the other, where it's going to pick the noise that sits on this space-time random variable. And you put a weight on the jumps, which is the transition probabilities of the random walk. Now, what happens in this? So this is a general fact. Now, one interesting thing that happens in the subcritical temperature is this separation of scales. So what it means is that these gaps here, all the fluctuations will be driven by the noise at very close distance to the origin, and to the alpha for any alpha less than 1. So this is the exponential time scales that appear also in the formulation of the result of Dunlap and Gu. So these exponential time scales plays a crucial role in the limit theorems in the subcritical temperature. One thing that happens is that so the noise actually will kind of cluster. It will create kind of clusterings where you will have a big jump into the alpha, and then all the other noise will be sampled by at distances n to the alpha prime, with alpha primes less than this alpha. So this distance here will be much smaller than all these gaps here. So you will have this clustering, and then there will be another very big jump, n to the alpha prime bigger than this n to the alpha, and then you will start collecting noise in a smaller region. So you have this clustering of the noise. And one thing that happens, and we showed with Francesco and Feng, is that all the collection of the noise, all the partition functions that you get here will converge to a Gaussian random variable. And then this blob here will converge to another Gaussian. So I don't know if it's correct to say the normalized picture that you see is that eventually you will have this kind of big jumps. At times, every time you get a Gaussian random variable. So this is some kind of flavor of renormalization. And then basically what you have at these states is the chaos expansion of a log normal random variable. And that's what leads to this exponential, this kind of, this maybe if you want an explanation why the exponential appears. Okay. Okay, so this is a picture in the structure in the subcritical temperature. At a critical temperature, this n to the alpha becomes irrelevant. So correlations become stronger at a macroscopic scale. I mean, all the action happens at order n. Okay, so before, if this is from 0 to n, before all the noise was constant, all the action was driven by the noise very close to here. So now at the critical temperature, you pick noise from every possible point. But still, there is a kind of, if you want, renormalization structure here going on. So the way to encode this is by performing a coarse graining. So you can split your space-time into boxes of length epsilon n and width square root epsilon n. So this is a space-time parabolic scaling. And then you can look, okay, maybe you visited this box and you picked up all the noise, and then you made a jump to another box, you picked all this noise, and then you made a jump to another box, you picked all this noise, and so on. Okay. But I don't know, maybe people who are very far away, actually, they cannot see the difference between this picture and this picture. So the two things look kind of similar, but there is a crucial point here, is that if you look at the disorder, so you can call all the disorder that's accumulated in a coarse grain block, you can call it maybe coarse grain disorder or new disorder. One thing that is crucial is what are the fluctuations of this coarse grain disorder. And actually what happens when you are at a critical temperature is that if you look at the variance of this coarse grain disorder, it has exactly the same critical scaling that like the original microscopic omega disorder that I was putting. So somehow, if you want, I mean, I'm doing some buzzwords now, and I think the term renormalization is probably very much abused. Maybe I'll abuse it a bit more and you can correct me, but somehow if you do a renormalization, somehow you are kind of at a fixed point. You see exactly the same thing like what you started originally. So, well, if this coarse grain variance has the same scaling like the original one, then this coarse grain model at a large n limit is basically the same as before. So I have taken somehow the limit n goes to infinity. Somehow this is a very rough picture, but there are many, many steps actually to carry out all these things. And yes, yeah. One of the steps, so actually what we would like to do is actually to take all this block and just replace it by maybe an independent normal random variable. Okay, so this procedure in probability theory is called Lindeberg principle. So that's probably the best way to prove central limit theorem. Central limit theorem is x1 plus x2 plus xn divided by square root n converges to Gaussian. Well, there is one distribution x for which the central limit theorem is trivial, and this is when x is normal itself. So the Lindeberg idea is, okay, you have some general distribution, and then you want to replace this, take this out, and replace it by a Gaussian, and then you want to see what kind of error you do when you do this replacement. If the error is not too big, you know the central limit theorem for normals, and then you can, by perturbation, you can get the central limit theorem for general distributions. So that's also kind of the idea here. We want to replace this very messy disorder by something which is just Gaussian. Okay, so if you do this, then basically you get your kind of scaling limit. So what underlines here is also a kind of a Cauchy approach to obtain a unique scaling limit. But one of the things you need in order to take this, remove it, and put back whatever you like, is actually to have control on the higher moments of your disorder that you want to remove. And so we need actually to control higher moments of the partition function and of this coarse-grained distribution. And yeah, this is also this is a mathematical physics conference, but I haven't put any diagrams. So I have to start putting some diagrams here. Okay, so if you look at what the thing that we need is a fourth moment. So if you take the partition function, you expand it, basically the fourth moment becomes actually a problem of collisions of independent random walks. So here you will have these four independent simple random walks in dimension 2. And then you want to see, how many times they will collide. So two of them will start colliding. They will start contributing to the fourth moment of this object. And then they will split. And then one will start colliding with the other. And then you have all these kind of collisions. And then basically controlling the higher moments corresponds to controlling finiteness of these collision diagrams. And so here actually methods from mathematical physics were quite very instrumental. So a way to go about this is to, go to some resolvent computation. And then basically look, okay, what happens here in the resolvent sense, and then what happens here, and then basically reduce this complicated convoluted diagram to a geometric series computation. So some of the operators that we need to control some type of LQ to LQ norm are this type. So here, so this is the resolvents. So summations over n e to the negative lambda n. The first diagram is when two walks collide before they split. So they start from positions x1, x2, and so on, and they end up at positions y1, y2, and so on. So we would need to control an LQ to LQ norm of this. And then you have, and this is something we had developed in some separate works with Francesco and Dongfeng, but you also have these very, very tricky operators. So these look simpler than the above, and in some sense they are. But yeah, it's quite tricky. Because basically, the problem is that if these 2 points come close nearby, so you form a loop here, which is basically the Green's function of a 2-dimensional random walk, and you start getting logarithmic divergences. So you need some way to treat this. And so here you see kind of the Green's function. So if you have kind of H random walks, each one lives in dimension 2. So it's the same as if you have a 2H dimensional simple random walk. And all these diagrams that I was having before basically reduce to the Green's function of this 2H dimensional simple random walk. And then you need where, two of them, they meet at the beginning, and then another pair meets at the end. So this is the depicted here. So you have two of them meeting at the beginning of the strip and two other meeting at the end of the strip. So you would like to have some kind of, some kind of inequality of this type. So here is if you have a function in LP, a function in LQ, then you need to control this bilinear form in terms of the LP and LQ norms. And this is a result we proved with Francesco and Renfeng without this precise constant. This precise constant came later with a work with another student of mine, Dimitris Ligonis. So if you have this kind of inequality in the bilinear form, this gives you an estimate on the norm operator, on the operator norm of this Green's function. And then basically passing to the resolvent is basically summing, the powers, a geometric series of the powers of these operator norms. So if you can control, then you have a geometric summable series. Progeny of this result was a result of Dell'Antonio, Figari, and Teta, where they looked at basically delta Bose gas. So the delta Bose gas is related to these collisions that I was talking about. So the moments of the stochastic heat equation, if you want, is a delta Bose gas. And the motivation of theirs was to be able to define a self-adjoint extension of this two-dimensional delta Bose gas. And so they had an inequality of this type, but in L2 for the Green's function, and we had to develop this in a different way. So our proof was more on the real space than in the Fourier space. In a more robust way that allows to go, that was very important to go to LP and LQ, because then we want to take, let's say, Q to be very, very close to infinity. So we were familiar with it. We knew this paper, but yes, there's sometimes a language barrier. So we were not able, there was some kind of lemma that there was not an inequality like this presented. But luckily, others, in particular, Ling Cheng Chai, so that was exploited in a paper by Gu, Castel, and Tsai, where they looked at the high moments of the stochastic heat equation, and they brought into the foreground this type of inequalities, but again in L2. Right? So they just used the inequality of Figari, Dell'Antonio, Figari, and that, and we had to develop this in this new framework. Okay. So a bit of a word to Allen-Cahn equations. Okay, so far in the stochastic heat equation, I had this, because of the linearity, the chaos expansion was represented by, it was kind of, you jump, it was directed. Now, if you go to nonlinear models, okay, how would you approach this? So you do Picard iteration, and then you end up with something familiar to most of you here, and much less to me. The solution can be represented as sums of this kind of trees. And this has to do with the Picard iteration. So if you put this thing back here, then you will get powers of this convolution with the noise, and then this gives this tree structure. When you are in the case where the noise appears only as an initial condition, this is the opposite to what Ivan was presenting in the last lecture. So the noise will only sit at the leaves. And actually here, I have drawn the leaves at different heights, but you should think that all these heights are time zero. Okay, it's a bit easier to draw it on ticks, on pixels. Yeah. So the solution of these objects, nonlinear objects, can be represented as sum of stochastic integrals. Ito integrals, no, it's not Ito integrals, stochastic integrals, let's say, indexed by such kind of trees. one difference between the pixel here and the pixel in the stochastic equation is that the noise is not ordered. So when you have space-time noise, you pick up the noise here, and the next one will be followed. In this case, the two noises actually can coincide. Okay, and this is a source that that leads to needs of renormalization and so on. So then you have this. Okay, so the stochastic integrals that I had in the previous slide, then need to decompose. When you have all these coincidences of the noise. So these are the constructions of the Wiener chaoses. So this type of integrals actually will decompose to a sum of this type of integrals where some of the noises will be matched. Okay. So it turns out that there is a particular structure. So you can have all different complicated matchings. But it turns out that the main contribution comes from matchings where every trident, so here the trees will be ternary trees because I had the U-cube nonlinearity. And the structure is that every trident will need to have an internal matching, a matching between. And then you can have nested matchings here. So if you think that you remove this internal matching, then you get another trident. Yeah, so you remove it here, you get another trident which has an internal matching. And there is this kind of recursive structure. And okay, there's quite a bit of work in the background here, and responsible for this is Simon and Tommaso. And there are some interesting mappings with cycles and so on. But eventually, you get the Gaussianity because you have all this kind of collapses, gradual collapses, that you do it in a kind of a iterative way. And then you get some kind of tree. This tree is deterministic. This red here will be logarithmic powers. It will be a logarithm here, which will cancel the logarithm of the noise. And then you will have one leaf that is unmatched, and then this will be the convolution with the white noise. And what's interesting is the collection of all these trees actually turns out to be the Butcher series or the B series of the SDE that I wrote at the beginning, which eventually gives the strength of the noise. Okay, so I think my time is probably up, and I'll stop here, and thank you for your attention.